Okay, thanks a lot. It's a real pleasure to be here. Thanks, Juan, for the invitation. It's really a pleasure to be here after some years. Okay, well, what I will talk about today is that the discovery of the first ever image of a black hole. It was a discovery that was announced on April 10th last year. And I would say this is a kind of dream, in the sense that when I started my PhD with John, I always have worked in the so-called very long baseline interferometry. That is a technique that offers you the best angular resolution that you can get, resolutions of the order of milliarcseconds. It means that you can see in the moons of the moon, you can see from Granada a coin of the size of a euro in San Sebastian. This is the kind of angular resolution that is offering. And in fact, my PhD is about the study of the relativistic jets that are emanating from the central parts, from the central engines of the active galactic nuclei. Of course, the dream at that time was to image the black hole for the first time. In order to do it, you needed to do a lot of things. The first thing you need to do is just go to very high frequencies, use the longest baselines that you could use, and of course increase the sensitivity enormously in order to see the very faint emission that is coming from these central regions. And when you read in the newspapers that this has been a work of at least 15, 20 years, this is the truth. Because it has implied an enormous development in the quality of receivers, in the refurbishment of the antennas, in the new software to do the data analysis, because we are going at the millimeter wavelengths at 1 millimeter. That means that the coherence time is very short, and that means that you need to integrate longer times, but you cannot do it because the coherence time is very short. Then you need a very sensitive antenna that you can use as an anchor to develop the whole technique in the interferometric array. And it has been the work of many years, many people, and these are the results. Then in that sense, I repeat, it's a kind of dream. What I will try to do today is just put this discovery into the context. Okay, the first thing, I will start talking about a little bit about M87, what we knew about M87 and what this image is giving us, what piece of information is giving us that we didn't have before. After that, I will mention all the details about the discovery. Then I will move, yes, to something that I think I am risking myself because I am here in the IFT. And then I will show some results and some discussion about the theory and about the challenges that are still open and how this discovery can contribute to solve them in comparison with gravitational waves and pulsars. And finally, I will make a kind of perspective for the future, talking about the work we are just now doing to study the black hole at the center of our own galaxy, the so-called Sagittarius A star. It will be my talk. I hope you will enjoy it. Okay. Of course, you know, this is just to give you one idea of what was the impact of the discovery. You know, that has been chosen by science as the scientific discovery of the last year. And you can see here the front page of many newspapers, a lot of newspapers around the world. Okay, I don't go into the details. Okay, the Galaxy M87. What's M87? Okay, let's do a trip. What's M87? If we go to the sky in the direction of Virgo, okay, there is a source there. We will see that in detail later in images, but okay. Yeah, no, it is. Here we have the Galaxy M87. It's an active galactic nuclei, a low luminosity active galactic nuclei is here, okay? You can see when we go to higher resolution, you can see you have this kind of loss of emission. When you go to higher resolution, you begin to see this relativistic jet that is going out from the central engine. When you go to higher frequencies, you begin to see just this stratification in the jet with this edge-brighten emission over there. And when you go then inside the galaxy, thanks to the EHT, what you have found out is the existence of this black hole. Okay, just to show you different images, just to give you one idea. Okay, this is M87. There you have the central engine, the central core, where the optical galaxy, where the host galaxy is. You can see that you have these relativistic jets. You can measure the velocities inside them. And in fact, you can see that here the jet is one directional. It should be two directional, but it is giving us already information that is very relativistic and that is oriented close to the line of sight, because you are seeing only one of the jets, and then Doppler boosting is enhancing the emission in this direction, not in the other. Okay, and you can see also that the jet is a clear evidence that the jet is decelerating when it's traveling through the intergalactic medium. Okay, because what you see is that the suddenly the pressure of the jet is comparable to the pressure of the external medium, and then it bends, okay, and it interacts, creating this kind of bow-shock structures with hot spots, etc. In fact, here is the jet is not relativistic, and then you can see both the jet part and the counterjet part, okay? This is due because the relativistic effects are not so important. When we go to higher frequencies, and with this is the VLA with baselines up to 27 kilometers. When you go to the VLBA, where you have, in this case, you have baselines up to 9,000 kilometers, the whole diameter of the Earth, and you go to 43 gigahertz, that means resolution of the order of 3 light years, you begin to see details. Let me mention one detail that is very important. When we go to very high linear resolutions, we begin to discover that these jets have a kind of a spine sheath structure, in the sense that you have a central region that is accelerated, okay? The central part will be this over here, okay? But you see this kind of edge-brightened emission also, that belongs to material that is not so relativistic, and that is probably coming from this material is coming from the accretion disk. However, the central part is more related to the black hole itself. Going to higher frequencies, 86 gigahertz with the GMBA, resolutions of the order of 0.3 light years, you begin to see this structure more clearly, as you can see here. And when you when you improve the resolution by a factor of 100, as you have done with the EHT, this is the image that you can get. Then what you are really imaging is the central area, the central engine. But really, we have learned a lot about jet physics with M87. You can see here, you can see the jet, how it's edge-brightened, as I have mentioned to you before. You can see some evidences of the counterjet. It's giving you orientation about the physical parameters as it's characterizing the jet. Here, look, we are here, yes, at the linear scales of the order of 500 spatial radio, 500 gravitational radius, already getting very close to the central engine of the source. And look, and we can do also images. I mean, these are images that have been taken alone a month. Okay, this corresponds to different epochs. Over here, you can see different epochs, and you can see how the plasma that is the relativistic jet is composed of plasma, essentially electrons, positrons, protons. Okay, and what you are seeing there is just the motion in these relativistic jets. And in fact, measuring these velocities, you get that the velocity, the inner velocity of these jets should be of the order of 0.99 c. That, in fact, is the escape velocity of a black hole, essentially. It was, for many years, it was one of the best proofs of the existence of a black hole. Okay, this is another important result that was obtained for the case of M87, and is what we call technically the core shift. And is that, these jets, as you have seen before, are formed by a central component, what we call the core, and this relativistic jet that is extending from it. But look, the emission that we are seeing here is essentially synchrotron emission. What we have is relativistic particles that are accelerated in the presence of a magnetic field. Okay, what happens is that the position of the cores depends on the frequency. Depends on the frequency. And why that? Because we know that the opacity is decreasing when we go to higher frequencies. Then the position at which the opacity of the jet is equal to unity, that is the position of the core of the source, is getting closer to the origin of the jet when we go to higher frequencies, as you can see here. The reason for that is very clear. While the jet is expanding, the magnetic field is decreasing, the particle density is decreasing, okay? And the opacity depends both on the magnetic field, on the particle density, and on the frequency. That goes to the factor nu to the fourth power. Then it decreases a lot when you go to higher frequencies. Okay. The first suggestion of this effect, of this core shift effect, is in the PhD of John Marcaide, by the way, but it was measured for the first time very carefully for the case of M87. And you can see that the position is changing with this kind of behavior. Okay, this is the general framework, and this is the result for M87. And you can see that measuring the position of here is the position of the core at 2 gigahertz, 5 gigahertz, 8, 15, 22, 43, and here the representation. And you see that when we go to already 86 or 100 gigahertz, we are ready, the position of the core is already getting very close to the central position of the source. Okay, it was a very nice paper by Hara, and he showed that the value of the position of the core depends on the frequency with this dependence. And in fact, you can obtain from this, if you obtain information about the magnetic field from polarization measurements, you obtain a direct measurement also, not direct, an indirect measurement of the mass of the black hole also. Okay, this is I would say, before the discovery of made by the EST, you can see here it is probably one of the best images at 43 gigahertz, where you can see what I have mentioned before, this spine over here, this edge-brighten emission. And it was just the prediction. Okay, this is a paper published in the year 2015 with the prediction of what we will see in case we go to higher frequencies. Okay, and you can see here that already we could detect just the so-called shadow due to the presence of the black hole, okay? In case we incorporate to the interferometric array ALMA. ALMA is the interferometric array that you know is situated in the desert of the Atacama. They are around 60 antennas, and if you combine all of them, you get the effect of one antenna of 70 meters. And it provides a sensitivity to be the anchor of the interferometric array, and it was key. Okay, it was the prediction. It's already published there. And, okay, and the final thing, yes, about jet physics, I want to mention that we have been able also to measure the jet width. Going to higher and higher frequencies and to longer baselines, we improve our angular resolution, and we can see the jet width at different linear scales. Look at this picture. Here what you have is the projected distance along the jet in gravitational radius. This is one gravitational radius. This is a black hole. Here you have 10, 100, 10 to the 30, 10 to the 4. And look, and what you can see clearly is that there are two kinds of slopes. You see that under something like 10 to the 4, 10 to the 5, you have a parabolic jet. This is the region where the jet is formed, is collimated, is accelerated, okay? And when you go to distances that are farther than 10 to the 4 gravitational radii, in fact, what you see is a conical shape, okay, indicating that the expansion is in equilibrium with external medium. Okay, this one is just the same. I continue. Okay, and now that's what we have got. After many years of work, observations performed on the year 2017, this is the result we have got. And in fact, this is the result that we thought that we were going to find, because essentially what we are seeing is, you see, this ring, this ring of emission that is due to the emission of the photons that are emitted by the material that is orbiting around the central black hole at a distance of around 5 gravitational radius, due to the effect of to the lensing effect. This is the size in which the photons are captured in an unstable orbit around the black hole. Okay, and what you see is that at the center, what you see is a shadow. And you see a shadow, a kind of black region, due to the fact that all the photons that are going with all the photons that are emitted by material that is accreting at a distance that is under 5 gravitational radius that corresponds to the photon capture radius, are absorbed by the black hole itself. And this is what we found. I can promise to you that the first time we saw this image, that it was summer 2018, almost a year before the publication. We were so happy. I mean, we couldn't believe that. It was a kind of, it was fantastic, really. And during many months, we were just keeping the secret, okay? Just to give you one idea, okay, this is what I have shown to you. This is the paradigm, okay? You have here the central engine of the source. You have this accretion disk with this red emission there that is a hot turbulent disk. You see these jets that are escaping with the escape velocity of the black hole. Velocity is very close to the C. And you can see here the EST image with this. This is, by the way, this is the size of the solar system. That means that the size of the Event Horizon telescope of the Event Horizon of M87 is larger than the case of the size of the solar system. You see this ring of emission, this ring of enhanced emission, okay? And this is the simulated image, because the fantastic work, something I want to mention, and it was not my field, by the way, but is that in the collaboration that is made of around 150 people, Okay, we have both observers, we have technicians, and we have people working in theory. Okay, and in fact, I mean, they have done a fantastic work just modeling the results we have got in order to at least give some basic parameters that can contribute to the knowledge of the physics of the black holes. By the way, look here. You have here the simulated image. Okay, this is the result of the general relativity magneto-hydrodynamic simulations together with radiative transfer incorporated to it. Okay, and you see, in fact, in these simulations you have the photon ring. This is the size of the event horizon of the black hole. Okay, and look, also that there is an emission inside, but this emission is coming essentially from the accretion disk or from the base of the jet. That's what we are seeing. But from the black hole, what we are seeing is just the ring over there. Okay, let me continue. And okay, after this summary of the physics we knew already about M87, we go back, and this is what we got. Okay, therefore we were going from the basic knowledge of the jet physics of M87 to the black holes itself. Yes, here it is. Here is the jet, and here is the Earth-Brighton jet with the central region, and here is our image. Okay? Okay, let's continue then. Give me now, please, I will give you some details about the observations. Yes, two basic things, you know much better than me about that. The first thing is, since we have we have around 10 to the 9 solar masses, what is happening is the light is bending. There is a gravitational line bending due to the presence of such a massive object. And we see also that there is a photon capture at the event horizon. Okay, we know that at the distance, I repeat, at the distance of around, due to the lens effects, at the distance of around 5 times the gravitational radius, all the photons that are, all the material that is orbiting around the black hole with a radius larger than this 5 gravitational radius, they will be just bent. All those that go just with this measurement of around 5 gravitational radius, they keep orbiting in unstable orbit around the black hole, and all those that are going with the impact parameter that is under this value will be absorbed by the black hole. Okay, then the image we have got is just the result of the gravitational light bending and the photon capture at the event horizon of the black hole. Okay, this is just to give you the black hole geometry. Look, up to now, what we knew is the jet. We have here our black hole. What we knew the jet. We know the ergos, okay, because this is a black hole that is rotating. This is a curved black hole. Then we have a region, that plays a relevant role. This is the so-called ergosphere. And this is very important because the particles can take from there can take a rotational energy and escape from the gravitational attraction of the black hole. We have the accretion disk, and we have also all these winds. Okay, what will be one of the next steps will be the connection between the curved black hole and the jet. But I will go into the details. And just to show you as a simulation, what are we imaging? Okay, yes, this is a nice animation that was done by the team of the EST, by our specialists. And you can see here, you see all the photons, okay? And you can see some trajectories that are just bent, and some others, when you go very close to this value that is around 5 gravitational radius, what you see is that all the photons keep orbiting in unstable orbit around the black hole. And what you see, from the point of view of the observer, you can see all these photons over there, okay, producing the ring of enhanced emission. That is what we are detecting. Okay. Okay, in fact, it was already published and proposed by Luminet in the year 1979. There is a very nice paper by Jean-Pierre Luminet in which he already, he already predicted this kind of observations. You can see here, look here, this is an image from his paper, from the original paper, now put in colors, of course. And you can see here the ring. And what you see here, this is the lens image of the accretion disk. Then in our case, we cannot see it because our interferometer is resolving completely the emission of the accretion disk itself. We are seeing only the compact part that corresponds to the last unstable orbit. Okay? Okay, this is the EA still. This is in Spanish. I have realized that this morning. Sorry for that. Okay, here you can see all the antennas that have taken part in our observations. You can see that there are antennas here in Granada. Pico Veleta, Noema didn't take part. This is the interferometer from Iran in France. Here is Pico Veleta. You can see here in Chile, you have both ALMA, the interferometer, and APEX. You have here in Mexico the large millimeter telescope. In Arizona, you have two telescopes, the South Millimeter Telescope in Kitt Peak. You have Karma there that didn't take part. And in Hawaii, you have also two telescopes, the South Millimeter Array and the JCMT. Look, it's very important that we have two telescopes here in Hawaii and two telescopes in Chile, in the sense that you can cross-check the calibration, first thing, and second thing also that you have a very short baseline that is very useful also for the calibration, for example, of the polarization angle, because don't forget that we are doing our observations in full polarization mode also, okay? Okay, in which were the objects to observe? Okay, the resolution, the angular resolution of such an instrument is around 20 microarcseconds. Okay, then in order to resolve the shadow of the black hole, we wanted to detect for the first time this shadow. We needed shadows that were longer than this value of our angular resolution that was of the order of 20 microarcseconds, okay? And the best candidates, of course, were Sagittarius A star, the black hole at the center of the Milky Way, and M87. Taking into account the difference in masses, in the case of Sagittarius, you know that the gravitational radius is proportional to the mass. It means since Sagittarius A star has a mass of 4 times 10 to the 6, and M87 around 6 times 10 to the 9, the event horizon is 10 to the 3 times larger for the case of M87. But it's farther away. You can see the distance. There is a factor of 3. That means that the shadows are very similar. And you can see here the shadows that are predicted. This is around between 47 and 50, and this is between 20 and 38. Then these were the real candidates to do this kind of work. And these were the objects that we were imaging in 2017 when we did the first observations with the AHT. This is the AHT, okay? You have all the different antennas. I continue, we have already seen that, and this one also. But let's go to this one. Here, what I'm showing here is, this is the equivalent dish to the whole array, okay? That is, okay, imagine, you have all the antennas, and all the antennas are producing one interferometer of the size of 9,500 kilometers. But of course, what happens is that this equivalent dish, we are not covering the whole surface, okay? Then what we can do is taking advantage of the rotation of the Earth and of the so-called aperture synthesis. Look, here you have all the different baselines formed by the combination of the different telescopes, and they are covering the whole surface of the equivalent dish. Okay, each of these points correspond to produce one of these visibility points that you get here. And here is the basic information. Here are the amplitudes, but we have also the phases. Okay, important information about the structure is here in this part where you have a kind of bump, as you can see here. It's very important to be sensitive on these areas because it provides very relevant information about the structure of the source. Okay. And also, look here, this is similar to the previous one. We are again generating the equivalent, okay, the equivalent dish, the equivalent telescope. But here you can see how the image is improving when you incorporate new data. I'm going to put it again. Here you have again how the whole surface is covered. And look, the interferometer, one interferometer formed by two telescopes at a certain time is providing information only about the structure of the source in one direction. Here, you can see at the beginning, you don't see the structure because you just see information about the structure of the source in one direction at a certain time. But when you improve the coverage, as you can see here, then you begin to recover the whole structure, as you can see here. Then it's very important to have very good UV coverage. Okay, let's continue. Okay, after that, what do? The interferometer behaves like a lens. What you get is, for every pair of telescopes, you get the interference pattern, you get the visibility function, and when you do just the Fourier transform, you recover the image of the source. Okay? And that's what we have done. And this is the image. Okay, this is the image we got. And let me mention some relevant aspects about it. The first thing I want to mention is that the experiment was repeated during 4 days. It was done in April 5th for 8 hours, April 6th, April 10th, and April 11th. And you can see that the image is just the same for the whole days, confirming the result. It was very good to do it during these 4 days. And in fact, you can see that there are no changes. There are no motions along the ring of material. Let's continue. Here, okay, this is just the meeting in which we obtained the first image. I want to show you. This is Harvard. This is at the CFA, the Center for Astrophysics, and the people we were working there. This is the image you can see. It was fantastic. It was July 18. Okay. Second thing I want to mention, we were using very different algorithms to recover the image. We were using the classical information we get in radio astronomy, that is the so-called cleaning procedure with the program diffmap, and this is the image that you recover. But we were using also other softwares that were specially developed for this experiment that are based on maximum likelihood methods, regularized maximum likelihood methods. You can see here the EHT imaging, SMILey. These are the kind of methods that are used, for example, for medical imaging. That was we were adapting it. I mean, we were just making a special case for these experiments, and you can see that the results are absolutely similar, also using different algorithms. Okay, and here, as mentioned again, 4 independent observations, all of them showing the same image of the shadow of a black hole. No variability during the 4 observing runs, as you can see. Here I want to mention the relevance of certain telescopes in the interferometric array. Look, here you have the full array when Chile is not considered in the image recovery. You can see how the image is completely diffused. You don't see anything about it. It gives you just the importance of ALMA, okay? And look here, without picobelleta, just the same. Picobelleta is in Granada, is providing the east-west resolution. ALMA is providing essentially the sensitivity. Picobelleta, the east-west resolution. You can see that when we lose these two, okay? When we lose picobelleta in Chile, the information about the image is completely lost, okay? But as mentioned, the next step was just try to interpret the image and try to get some physics of it, okay? It's not only the case that what was proposed by general relativity in the sense of having this photon ring, this ring of enhanced emission, okay, and having the shadow was there. We were trying also to get some physics of it. And we were doing just simulations, combining both, as mentioned before, the general relativity, magnetohydrodynamical modeling, and also the codes of emission incorporated to it. And you can see it here. This is the image of April 6. This is the reconstructed simulation, and this is the image that we get from our simulation. You can see they are very, very, very similar. What we were trying to do is we were fixing the parameters of our modeling in order to reproduce the visibilities, the interferometric observables, okay? And the modeling was based essentially in the determination of several parameters. The first one was the spin. This A star that is there is just the ratio between the spin and the mass of the black hole, okay? Another parameter that we were using, of course, was the magnetic flux, just the comparison between the magnetic flux and the accretion flux. And the third one was, of course, since, remember, the emission that we are seeing here at 230 gigahertz, Synchrotron Emission, is distribution of protons and electrons, distribution of relativistic particles. And we need to know, in order to do it, also the temperature of both. This R parameter is just providing the ratio between the temperature of the ions and the temperature of the electrons. For the very high magnetized regions, that means, for example, in the spine of the jet, they are similar. But for the disk itself, it's not the case. In this case, for ions, the temperatures are higher. Then you can see here different reconstructions, okay, for different modelings, and you have also this sane and these matte models. The matte models corresponds to magnetic arrested models. That means very highly magnetized, and you can see here this sane corresponds to normal values of the magnetic field. Then we were just doing a lot of simulations, really. I mean, okay, and this is what we get. Okay, this is the simulated image. We will see some details after that, just to make it clear. You can see here the simulated image result of the numerical simulation, and you can see the EHT image. Okay. We were able to determine the rotation of the with the modeling, we could determine the rotation of the material in the disk, in the ring, okay? Determining the rotation of the material in the ring, we were determining also the orientation of the spin that was directed away from the observer, okay? You can see here. And you can see here in both images the even horizon determining our experimental image and the even horizon determining the numerical simulation. You can see there is no emission, okay? And I continue, and you can see now the bright emission ring. And I repeat, all the emission that is inside correspond to the base of the jet and to the accretion disk, essentially, okay? Not to the black hole itself. With all this information, we could determine these image parameters. The ring diameter is 42 plus minus 3 microarc seconds, coinciding very well with the shadow that was predicted. The ring width around 20 microarc seconds. The contrast is 10 to 1, the emission of the ring compared to the emission of the central part, and the circularity that is providing important information about the quadrupolar moment also of the black hole. And we could determine that. And in fact, I mean, this value of 42 microarc seconds corresponds very well with, taking into account the distance of the source, the mass, and this increasing factor coming from the lensing effect. We could determine very nicely, in fact, all these parameters, okay? And we were performing numerical simulations, as mentioned, playing both with sane models, with magnetic models, with different values of the spin, different values of the magnetic flux, etc. And these are just some examples of the simulations. You can see some simulations that correspond essentially to the same cases in which you can see that the size of the emitting ring is much wider, okay? In others, it's much narrower. In others, okay, we were producing more than 60,000 simulations to produce 60,000 models in order to obtain the best fit to our observational values. And this is what we got. Okay, you can see here the parameter, okay, the parameter, the determination, and that's what we did. I will go back to it. But imagine then, these are our results then. Look, this is, for M87, there were two determinations of the mass up to now. One was coming from the stellar dynamics, from the determination of the stellar dispersion velocities. And this mass was around 6.5 to 10 to the 9 solar masses. And this is the size of the static black hole for in the case of the Schwarzschild black hole for this mass. Okay? If we consider the Kerr black hole, taking into account the angular momentum, it's a little bit smaller. You know that is due to rotation, it gets smaller. This is the value we get. If we consider the mass determined from gas dynamics many years ago already, it was determined by Duchamp Maqueto around 79, in fact, for M87 also, with this mass, okay, sorry for that, and this is the combination of both of those, sorry. Now, taking into account the gas dynamics, these are the sizes that are determined, as you can see here, okay? If we consider the case of a, oh, sorry, worm, there is an error there, okay, a wormhole, this is the size, around 2.7 gravitational radius, sorry for the A. We consider just a naked singularity, this will be the size, just a gravitational radius. And this is our image. Okay? And then from these measurements, we could exclude all these other possibilities, okay? And guess, and determine and clearly that M87 contains a Kerr black hole with a mass of 6.5 to 10 to the 9 solar masses. Okay. Confirming Einstein general relativity theory. Okay, which is the future with the EHT? Before going a little bit more, I know that I am in the Instituto de Física Teórica, then I will go a little bit deeper in the theory part, okay? The future, which will be, look, up to now, what we have seen is just the black hole here in the central part and the jet over there. But we need to know the black hole jet interface. Just now, we think that we are favoring the so-called Blanford-Snajek models in the sense that the energy, the rotational energy that is produced in the jets is taken from the black hole rotation. It's anchored to the black hole rotation. That's what we are suggesting here, but it would be great just to see this interface because it will be the final confirmation, okay? And we think that it is the case because look here, this is an image done with a so-called global millimeter VLBI array at 86 gigahertz, and you can see that the jet base has a width of around 30 Schwarzschild radii between. Okay, this is the size. And the edge brightened jet has a transversal width of 70 Schwarzschild radii. Then it is really suggesting that the relativistic jet is anchored to the rotating black hole. Okay. Some starting points for the theory analysis. What we are measuring, that are the visibility amplitudes and the closure phases. Look, we don't have the phases. And this is important compared to other interferometric experiments. We don't have the phases, and we don't have the phases because the coherence time is so short, okay, that we could determine only for certain baselines, but we don't have all of them. We also know the image domain features. We know that there is a ring-like geometry. We have determined the brightness temperature, the total flux, the asymmetry. We have also prior constraints. These prior constraints are coming from the jet power, we will solve it later, and the X-ray luminosity. But we want to know what are the physical implications of these image features. Okay. Which are our simple estimates to start our interpretation? The first thing is we hypothesize that the source is a black hole. First thing, could be the case, could be a boson star, could be a Granada star. We are hypothesizing that it is a black hole. We are considering also black hole accretion systems, and we consider that is described by its mass, spin, magnetic field strength, accretion rate, the microphysics, electron-ion thermodynamics, inclination, position angle, etc. Because we are combining, I repeat, the GR-MHD together with emission codes. We are modeling the source as homogeneous and compact, okay, with a spherical radius of that. And here you have some parameters, or typical parameters that have been determined. Typical mass accretion rate for a low luminosity AGN, 10 to the minus 5 Eddington. There's the ratio between the ion to electron temperature ratio, etc. Typical values, okay? And this is what we are doing. We are taking the GR-MHD simulations coming from the black hole spin and the B field configuration. We're describing the fluid by the density and temperature, velocity, magnetic field. And we are just resolving the emission codes and making the general relativity ray tracing, taking into account the inclination of the disk, the orientation, thermodynamics, etc., in order to produce the images. It has been the process, okay? Priors, we know that the jet power is 10 to the 44, between 10 to the 42 and 10 to the 45 ergs per second. And the models must produce this energy outflow. Okay, although we are imaging only the central part, they should be able to produce this energy outflow. And we are assuming that in fact, the jet power is produced by the Blanford-Snijek process. Okay, what happens? The black hole is dragging space as it spins, and the magnetic field is frozen, okay, with this material. And then it means that the magnetic field lines are also dragged and bound up in the jet funnel region, okay? And then all the energy, the outward energy is coming from the Poynting flux. Okay, and the first conclusion that is very clear is that there is no good simulation assuming that it is an static black hole. It needs to be rotating in order to produce this jet power. Okay, these are different models. I don't go into details. I prefer to go into this one. The second conclusion that was very important to determine is that the brightness of the image is produced relativistic velocities. We are, of course, affected by the aberration of light. That means that we have the Doppler boosting. And then we can determine that the brighter part of the image, that is the southern part, corresponds to matter that is moving towards the observer. Okay, and then in our models, second thing that we have determined is that the emitting material is rotating with the black hole. And then in that sense, it acts as a signature of the sense of the black hole spin. Okay, and this is something that we are also determining from here. Look, here we have been able also to compare the different results we get for the case in which the hole and the disk are co-rotating, and for the case in which the whole of the disk are counter-rotating. This is for MAT models. Remember, MAT means very high magnetic fields. SANE means normal magnetic fields. And look, for the case, you can see here, this is the orientation of the observer. The spin goes in this direction, okay? And you can see that in the SANE models, in general, produce very wide jets. That is not our case. In that sense, we are also favoring, okay, MAT models, okay, in fact, with low values of R. Okay, and here you can see that for the case of the counter rotation, you don't see these very well collimated jets that we find in the reality. Okay, then it's a very good also constraint for our models. Okay, and finally, I mean, I would say that the main conclusions for then from the point of view of theory are the following. The first is that the data are consistent with the image of a curved black hole. It needs to be rotated. Second, however, our simulations are not able to exclude many families of models. We have a whole family of models that are consistent. Polarization will give us an extra information that we'll be able to restrict them. Third, all the models are consistent with black holes with non-zero angular momentum and with the Blandford-Snijek mechanism as a way to power the jets. And finally, the image asymmetry is driven by the spin of the hole, independently of the disk motion. Okay. Look, this is the scenario. Where are we? Look, this is the gravitational phase space argument. Here we have the curvature strength, defined as m divided by L cubed, okay, the square root of that. For the case of a black hole, since the size goes is proportional to the mass, okay, what we find is goes to as 1 over m. And here you have the field strength, which is the space parameter that is checking our experiment. Is this one over here. You can see for the field strength quite strong. Look here, this is the EHT data, okay? And for the curvature strength of the order of 10 to the minus 8. Just to give you other experiments, you can see yes, the gravitational waves from ground are checking similar values for the field strength, okay, and strongest curvature, okay. For the case of the double pulsar or binary pulsars, we are over here with the determination of the Shapiro delay and the gravitational redshift here in the double pulsar. We're here. We are not checking values so high for the field strength. We are over here. Okay. LISA will produce results over here. This is gravity, the instrument of the VLTI, with the orbits of the stellar, with the stellar orbits of the stars that are close to the black hole. We are in this area. In that sense, the EHT potentially is a very interesting instrument because we are really at very high values of the field strength. Okay. However, if we check that, I mean, we can compare those methods. Huh? Probably you know many of these details much better than me. I have tried to put together some details, and in fact, when Juan has seen that, he has made the first correction in the first line. Then, but just to give you one idea, no? With the gravitational waves, we have some strengths. We are taking the conservative and dissipative dynamics at the high post-Newtonian order. Is valid both for neutron stars and stellar black holes. Is seen more non-linearity, etc. Weaknesses. I thought that it could only access 100 solar masses systems, but Juan has told me that it's 140 already. 140, something like that. I think that what is very important is that the weakness of this test is that it's a very short duration event and it is not going to repeat. Okay? Then one event you are going to see it one. So the next one is that it's very difficult to degenerate the spin, to break the spin degeneracies in both cases. Okay, going to the binary pulsars. In this case, it's very good to constrain post-Newtonian corrections. In fact, all the post-Keplerian parameters have been determined with a very high precision for the case of the double pulsar. Okay? In fact, there are a number of sources, more than 20, for which this kind of work has been done, and you can see the Shapiro delay. Okay? However, the weaknesses, you are checking only the test gravity in neutron stars, okay? You are not going to black holes, what I have mentioned before. We are in the field strength, we are lower values, okay? And with the black hole shadows, which is the advantage? The first one is that you are seeing the interplay between the electromagnetic radiation and gravity, okay? And we are in fact playing with high electromagnetic energies, okay? I think what is important, we have the ability to see the same source indefinitely. We are going to, the observations I am showing just now were performed in 2017. there were observations in 2018 that are just now under analysis, and there will be new observations in 2020. Then we will be able to check subtle effects, okay, and changes in the image that could be interpreted, okay? However, as mentioned here, I didn't find another word to mention that, messy astrophysics. We are mixing magneto-hydrodynamics, turbulence, many fields, and it's very difficult to discriminate between them. Here is how to test the first, okay? You have different questions that the different methods can answer, okay? The gravitational waves, the binary pulsars, and the black hole shadows. Let me go into the black hole shadows, okay, in order not to be too long. And in fact, the question is, how close to the curve metric is the exterior space-time of supermassive black holes? This is the answer that will be given by our observations. Okay, the problem is that the high curvature modifications to occur are too small to be constrained with AHT. Okay, then it's in certain way, from the point of view of the pure theory in testing GR theory models, is okay. Still the things have to improve in order to make really valuable information. I would say that it just now is complementary also to the others, because in fact there is a nice result. This gravitational waves is giving information about stellar black holes, and here we are getting information about supermassive black holes. Then we are checking GR at different masses, and we could check whether there is a linearity in the behavior between the different scales of black holes. Okay. And what's next? Yes, I'm getting to the end. The next, of course, is Sagittarius A star. When it was given the announcement that there was going to be just a press conference to show the first images of the black hole, I think everybody thought that it was going to be Sagittarius A star. Okay, Sagittarius star, yes, very brief information. Look, this is the Milky Way in infrared. Okay, these are 1,000 light years. Okay, you have a lot of sources. You have stars of different massive stars, very low mass stars, old stars, young stars, and here you have the galactic center is just there. Okay, when we go to just passing from 1,000 light years to 18 light years in the central region, here is where is the Sagittarius A star, the central black hole. When we go to only 4 light years, look, you have still 10,000 stars, 10,000 point sources, close to the black hole, okay? This is the image in radio. This is now 1,000 light years again. The first image I have shown in the infrared, but now in radio. And here you have the galactic center over there. But look at these images because it's really beautiful. Look, you have stars. You have supernova remnants that are stars that are dying. You have all these areas that are star-forming regions, okay? You have all these filaments that are tracing magnetic fields, okay? And you have here the galactic center, okay? Let's go. Okay, here you have the same image, but with better resolution. I mean, it's the same image. Okay. Look, the energy that is produced at the galactic center produces these bubbles, okay, that are expanding. And you can trace them in radio. Okay, but what is important is that in radio, what we know is that there is a source. This is at 1.3 centimeters. There is a compact source at the dynamic center of the galaxy with a mass of around 4 times 10 to the 6 solar masses, and that has a size that is smaller than 1 astronomical unit, because the Schwarzschild radius for the black hole at the center of our galaxy is around 0.08 AUs. We are getting closer, okay? Also, the advantage is that we know that we have information also, okay, about the orbits of the stars close to the galactic center, or to our galactic center. You can see here, this is the star S2 that has already completed an orbit and has been studied by astronomy. The period is around 18 years. More than one, the orbit has been covered already for 22, 23 years. And we have seen, in fact, the precession of the periastron, of the source. Here, just to show you a picture, yes, of the last data points. Okay, there you have the event horizon of the black hole, and here you have the star S2 orbiting around it, and you see how it gets accelerated when you get close to it. You can see it here, all the details, okay? This is to give you here, you see the whole orbit, okay, with a radius of 400 astronomical units, the closest approach over here, okay. The second important thing about the source that was already new is that the source is variable in the infrared. You can see this is the source. In the near infrared, it's changing, and with periods of minutes, as you can see here. That it means that it's accreting material and changing the accretion rate very quickly, okay? And which is the information we have up to now from very long baseline interferometry. But what we have is this one. These are observations at 86 gigahertz with a resolution of 87 microseconds. And this is the image you get. And as you can see here, essentially what you are seeing is a compact source with a size of around 120 Schwarzschild radii, okay? However, we have some information a priori, some testing observations at 230 gigahertz that gave us information that the size of the source was smaller than 4 Schwarzschild radii. It's coming also from preliminary observations at 230 gigahertz before the EHT, but with very short baselines. The question was, is this emission, I mean, this 4 Schwarzschild radii corresponds to a compact source at the very center or corresponds to material that is orbiting around the compact source? What is the emission that we are seeing? We were not able to image it. We were able just to make a model to the size of the source. That's what we will see in the next future. But meanwhile, and that's what I have mentioned to Juan before coming to the talk, there has come a beautiful result coming from the gravity VLTI collaboration. In fact, look, I try to explain to you that. What you see here is the flux of Sagittarius A star in the infrared, and you can see how it's changing continuously. It's increasing and decreasing, okay? And this corresponds to a second event over there, okay? And look at the period. These are 20 minutes. I don't see it from there. 30 minutes, okay? Look how then the flux is changing. And the interesting thing is that they were able to determine the astrometric position of the source. And what Gansel and his group show is that the position was not stable, was wandering around the position of Sagittarius A star. And was wandering with an amplitude of 150 microseconds. But the funny thing is that, I mean, this wandering, this motion was not just casual in the sense that it was moving from one side to the other, no. There is a correlation between the different epochs of, the different observations corresponding to different minutes and the positions of the peak. And as you can see here, there is a rotation in this motion, okay? This is not random motion. This is well-ordered motion, describing, as you can see here, a trajectory, I mean, a kind of orbit of the size of 150 microseconds, okay? That, okay, as you can see here. And at a distance of around, look here, should be here, 7 gravitational radius. Okay? Then the astrometric precision they were getting with gravity, with the instrument, permitted to determine gas motion, okay? Or accreting material, let's say it in that way, accreting material at a distance of 7 gravitational radius. And in fact, rotating, as you can see here, I mean, it's, oh, excuse me. Okay, as you can see here. But the fantastic result also is that they were also able to measure polarization in the infrared. Okay, and you can see here how the polarization was changing. This is degree of polarization, okay? It was changing, as you can see here. Okay, here you have here the intensity, okay? And look, in this graph here, we are representing, well, they are representing, I would like to do this work, but I haven't done anything here just for the EST, but not here. And you have here the Q Stokes and the U Stokes. And you can see how Q and U are changing also systematically, following again a clockwise rotation with the same periodicity that the astrometric position of the source. Okay, then it's motions, I repeat, of 150 microseconds over a few tens of minutes at 30% the velocity of light. And at the same time, the flares exhibiting rotation of the polarization angle with about the same period. Of course, then imagine, the information that this is giving to us is that the source is changing every 10 minutes because it's doing a whole cycle in 45 minutes. Then the source is not the same now and 10 minutes later. Then it means that our interferometric data, we cannot analyze the whole set of data at once because the source is changing. And then we are committed the error, then we are going to get a kind of blurred image because we are seeing different images every 10 minutes. Okay, then it means that this is the problem we are getting with the EST data just now, that we have to combine our reconstruction images with the light curve. And we have to do a kind of dynamic imaging, okay? And that's something we are working on just now, following different approaches, okay? Because the source is, and then what you will get, I hope, probably at the end of this year, okay, will be just a movie of the black hole at the center of our galaxy. Because you can get an average image, but you cannot get an image because it's changing every 10 minutes. But besides that, there is a second problem also, and it's that the Sagittarius star is in a very dense region. To observe Sagittarius star, we have to observe the whole galactic plane, and it's full of dust. And then what it produces also is it distorts, it produces scattering of the image. Okay? Then, although at these high frequencies is quite controlled, we still have an effect because, and we have to correct for it. Then these are the two problems that have done that the image of Sagittarius A star have been delayed with respect to M87. Okay? In M87, remember, when I showed the properties at the beginning, that during 5 days, this is the accretion period. We know that the accretion period is longer than 5 days. Then we can integrate the data along a day without any problem. Okay? Okay, that's then calendar. Keep the eyes open because I think that the results on polarization of M87 will be coming around June, July, around summer, let's say. And the results of the dynamic images of Sagittarius star will be coming at the end of the year, beginning of next year. Keep tuned because they will be coming and they will be great. Okay. These are the simulations we have up to now. We have data also, but this is the simulations for the case of static black hole, for the case of a rotating black hole. Okay, this is what we get. Okay. And okay, this is the. I put this image because it's a kind of symbolic image, because when we proposed for the first time to NSF and to Europe, the performance of the observations with the EHT, it was the image that was in the front page of the proposal. Okay, it's just like that. Okay, and I think Juan has already seen that, and it's a slide I always put just to finish my talks about the EHT. It's a sentence that is supposed to belong to Albert Einstein, in which he says that incontables experimentos podrán probar que tengo razón, pero un único experimento bastará para demostrar que estoy equivocado. And okay, for the moment, we can say that the EHT up to now has confirmed what Einstein was proposing. And thanks a lot, and sorry for the quarter of an hour of losing your time. Sorry for that.
Thank you very much indeed, Antxon, for a very nice talk.
Okay, so you just said that it is a rotating black hole. Can you say something about the electric charge or something?
Then?
About the electric charge of the black hole. Is there a chance to have a Reisner-Nordström black hole?
We are not sensitive with the EHT to the charge. No,
is that something which will be take into account in future experiments?
Not really. I don't think we can constrain that really. No, it's something we cannot constrain, really. I mean, because what we are seeing is synchrotron emission, okay? When what we can constrain is the population of relativistic particles, etc. But about the charge of the black hole itself, we are not sensitive in that sense.
So the electrically charged fluid around the black hole will not be influenced by some charge of the black hole, even if the charge is very high?
Look, you have to understand that what we are seeing here is not the electric charges of the black hole itself. We are seeing just the material, okay? We are seeing the material that is accreting, okay, towards the black hole. We are seeing, let's call in that way, the last stable orbit of material, okay, accreting towards the black hole. That's what we are seeing.
But this material is electrically charged, no?
It's electrically charged. It's a plasma, yeah.
So
it's a plasma.
it should be influenced.
We can check different population of different electron population, electron distributions, okay, and this kind of things. But really, we are considered, no, I think we are not sensitive. We consider at the end is neutral what we are seeing here, essentially here, okay?
This is just only to make sure that I understood this.
Yes.
At the moment, you say that the image is a Fourier transform of the interferometer data.
Yeah.
That means that the data are the Fourier transform of the magnetic field.
The data are the data are the interference pattern. Is the result of the interference pattern of the two telescopes, of every combination of two telescopes.
Okay.
This is your data.
But if getting the Fourier transform, you
Yes.
get the image of the black hole, of the
Yes.
magnetic field, that
Yeah.
means that the data are themselves the Fourier transform or the inverse Fourier transform
Yeah.
of the magnetic field.
Yeah, okay. No, wait. Yeah.
And then the simulation that you showed to us are obtained with the magnetohydrodynamic.
Sí. Yes, magnetism is taken into account. Fully taken into account.
So it's a simulation of the curve singularity with the magnetohydrodynamic.
Yeah.
Oh, sorry, I want to just...
Yes. No, in fact, it's one of the key rules. Imagine, for the magnetohydrodynamic, there are two key parameters. The first one is the spin, okay, in fact, the ratio of the spin with respect to the mass. And the second one is the magnetic flux, the ratio between the magnetic flux and the accretion rate of the material. Okay? And besides that, we are playing both with two families of models, the so-called SANE and the so-called MAT, the magnetically arrested disks. In this case, which is the main difference, essentially, is that for the MAT models, both ions and electrons have the same temperature in the whole structure because essentially everything is magnetized. And for the same ones, now you have to consider separately the disk and the funnel and the jet, because in the jet they will have the same temperature but not in the disk. Essentially, this is the difference.
I have a question.
Yep.
The jets go in the direction of the angular momentum?
The jet is going, in this case, yes. And in fact, as I was discussing with Juan this morning, it provides relevant information now because, good question, no. Okay, let me see. Yes, the jet, yeah, good question. Yeah. The large-scale jets, as you have seen, is not in the, I come back perhaps to, let me show you. Okay. The jet, the well-known jet, for which, for example, it was determined, meanwhile I continue, the first determination of the mass of the black hole for M87 was done in 1987 by Tushio Maketo using data from the Hubble Space Telescope, measuring the velocity of the gas, okay? That was around 550 kilometers per second at a distance of, I don't remember exactly, okay? And in this case, you can see that the jet is following the direction that is towards the northwest, okay? However, here, look, I mean, we are seeing, this is our black hole. Then in principle, the direction of the magnetic rotation axis is this one. Then it means our hints are the following, that the few hints we have from this image show that there is the putative emission of the jet is leaving the source in this direction and bending towards the direction of the larger scale jet. Okay, but the larger scale jet, you're right, it's in this direction. Let me, I don't want to touch anything, just in case. Sorry for that, but yeah, sorry, let's stop there. Okay, then our hints, I repeat, our hints of the jet coming from the EHT observations are coming from, indicates that the jet is ejected in the direction of the angular moment axis, yes.
I have an even more naive question. The backward jet is not visible for any reason. I didn't get it, even you mentioned, or it's not there. I mean, what is the, what do you know about backward?
Yeah, the counterjet, you mean?
Yeah, I mean the cut.
Oh, sorry, I would like to show you the image, and then you can see that.
You can risk to go.
Yeah, I prefer not to touch. Sorry for that, but we can see it later in the computer.
No
but in fact, we see the counterjet in at 86 gigahertz, where we have a very high sensitivity, and we see that it's there, but the ratio of the flux of the jet and counterjet is over 10 to the 2, 10 to the 3. That's already giving you information about how relativistic is the jet is. Okay, it's giving this information. Is there? One of the things we were discussing, as taking advantage of your question, was the following. I mean, we wanted to be sure that what we are seeing is really the black hole, okay? There's the shadow of the black hole, okay, with both elements, both the enhanced region of emission and the dark region at the very center. But we were considering other possibilities. And in fact, we were considering the possibility that what we were seeing perhaps was a kind of, we were seeing the counterjet lensed by the gravitational potential of the black hole, okay? It was, in fact, a kind of Einstein ring of the counterjet, okay? It was one of the possibilities we were discussing, but it cannot be. I mean, it cannot be because it should change. I mean, it should have some properties that is not the case. But it's a very good point, your point. I mean, with high enough sensitivity, we do see the counterjet. Not with the HT, obviously, because we are seeing only the black hole. But when we go to higher frequencies and to very high sensitive observations, we can detect it. Yes. Just taking advantage of your discussion also, you could ask me, are you restricting any other possibility and any other interpretation besides a black hole for the image you are getting? Because in principle, the only thing we can say is that anything, I mean, any compact emitter, okay, that is able to produce a kind of unstable photon ring around it is consistent with observations, okay? And it could be different cases. We have seen that wormholes and naked singularities cannot be because they would produce a much compact footprint. What about boson stars, for example? In the case of boson stars, you could produce this image. In the case of boson stars, you don't have an even horizon. You don't have also a kind of wall like in the normal stars. Would it be consistent? We don't think so because of the following. In the case of a boson star, and correct me because you know much more than me about it, what happens is that the geodesics, I think, can go out of the gravitational field of the central source. And in this case, could happen that due to this, some of the mission could go towards the central region, thanks to the existence of these geodesics, and we don't see anything there, okay? Referring to Grava stars, in this case, we also don't have the even horizon. We could have a limit of the star itself, okay? But in this case, just with one image and with one epoch, we cannot discard between both models. And it's still, I mean, it's less probable that the black hole as we have seen here. But what is sure is that with observations performed three years later, in checking the comparison between different epochs, should be, we must be able to see the difference. Because look, what is clear is that we know that M87 is variable, okay? The source is variable. It changes the flux. It goes at 3 millimeters, 86 gigahertz, and even at 230 gigahertz at 1 millimeter, it changes from 0.7 Janskis up to 1.5 Janskis. However, our hints are that although the flux is changing, the size of the black hole is not changing. Because we have previous observations, only models. What I have shown for Sagittarius A star, you remember, I mean, I told you that there were some previous observations in which we could do only model fitting and determine the size of the compact region. The determinations we have for M87 also coming from model fit from previous observing epochs give us the same size we have determined now with our experiments. And the flux was very different. Then it means that it has not, although the flux is changing, the size of the black hole is not changing. And it's not changing because it depends only on mass, okay, on angular momentum. And it's a very good confirmation.
You're observing changes in flux.
And flux,
mass, which falls onto the
that's the point. Yeah, but the size itself, exactly.
This is especially a question because in all your presentation you insist that this is a Kerr black hole.
Yes.
But as you mentioned right now, when you just gave the estimates about the size and gravitational radius, you never introduced an angular momentum.
You know, very good, very good point. You know, the difference, I don't want to touch that, sorry. You know, the difference in the size, considering rotation and non-rotation, is only of 10%. You remember that what I have shown, yes, at the beginning, the models, first for a static black hole, and then for a rotating, that is, and then at the end, what I put is just a wider circular shape, okay? Because the difference is very small. But I can tell you that you cannot produce this outflow energy from the jets from 10 to the 40 to 10 to the 45 with a static black hole. I mean, it needs to be rotating. This is, I mean, there are some conclusions from theory that are clear. First is that it is rotating. Second one is that also the material is rotating clockwise, in the clockwise direction. Third is that the angular momentum is in the direction away from the observer, from the screen, okay? These are three parameters very well determined by the models. These are clearly.
And you can really rule out the vaccine?
Yes.
Just because of the jets of the material?
One of the things, this is one of the key points, yes, that you cannot produce this outflow energy, this point in flux, this point energy with a static black hole.
Okay, I think we could stop here. Thank you very much.
Okay.
Again.
Thank you. Thank you. Thank you.